3.8 and 3.10 practice problems. Based off of the concepts of polarity and hydrogen bonding, which of the following sequences correctly lists the compounds above in order of increasing solubility with water? So remember that water is going to be highly polar, and so I am going to look for the most polar compound is going to be the most soluble, and the least polar compound is going to be the least soluble. So carbon and hydrogen is a nonpolar bond, so this is going to be the thing that I am going to expect is going to be my least soluble compound, so I'm going to eliminate anything that doesn't have X as my least soluble compound. Then looking between compound Y and compound Z, I see that compound Y has one hydroxyl group and compound Z has two hydroxide groups, and so the more hydroxides, the more polar. So Z is going to be my most polar compound, so option E is going to be my correct choice since it is the most polar. Benzene, C6H6, has the structure shown above. Considering the observation that benzene is only sparingly soluble in water, which of the following best describes the intermolecular forces of attraction between water and benzene? So as I look here, I see that we have carbon and hydrogen, which is a non-polar bond. However, and we also have this this nice ring here where we have double bonds and single bonds. This can also be represented with a circle since we are going to have some hybridization there. And we see that it is sparingly soluble in water, which means that it's not insoluble, it just is a little bit soluble. So that means that it's not completely exhibiting non-polar characteristics. We're going to have some polar characteristics. We're going to have some amount of interaction between water and benzene. So A is going to be eliminated since we know that it can dissolve at least a little bit. For the benzene and the water, we are going to have the water molecules come over. We can form some hydrogen bonds here between this hydrogen and this oxygen. That is true. However, this is going to be a very weak hydrogen bond, seeing as this hydrogen is bonded with a pretty non-polar carbon here. So it's going to be a pretty weak hydrogen bond, probably not what's happening. Benzene being hydrophobic means that it's not going to dissolve at all, so I'm going to get rid of that. And so I am left with my options being that the hydrogen atoms in benzene can form hydrogen bonds with the oxygens, or that I am dealing with dipole-induced dipoles and London dispersion. So London dispersion is always going to be present, and then since I have a permanent dipole here, I can pull and create another dipole here. So very weak hydrogen bonds versus London and induced dipole. London and induced dipole are a better explanation for what's going to be going on and why we have some measure of solubility, just not a whole heck of a lot. On the basis of molecular structure and bond polarity, which of the following compounds is most likely to have the greatest solubility in water? So we are again looking for the most polar of the compounds. So carbon with 4 hydrogens is very non-polar. Carbon with the 4 chlorines. Chlorine and the carbon bond is a polar bond. However, I am very symmetrical, so that's also going to be non-polar. So I am left with nitrogen with a trigonal pyramidal shape, or phosphorus with a trigonal pyramidal shape where we have hydrogen here. So these two structures look very, very similar. So between the two, I can't tell it based off of symmetry. Instead, I need to tell it based off of electronegativity difference. Since nitrogen is higher up on the periodic table, it is in row 2. It is going to have a higher electronegativity than phosphorus, being in the same group. So since nitrogen is going to have a higher electronegativity, therefore have a higher electronegativity difference between hydrogen and nitrogen, this is going to be my more polar compound. Sodium chloride is the least soluble in which of these following liquids? So sodium chloride is an ionic compound. We have full charges present, and like is going to dissolve like. So if I want something that does not dissolve things with charges, I want something that has no charges. So something that is incredibly non-polar. Water is known to be polar. Carbon tetrachloride, just like we talked about with the last problem here, even though the carbon and chlorines do have a polar bond individually, we do have a non-polar system since it is symmetrical. Hydrogen and fluorine is going to be very polar. The hydroxide group is going to form a very polar compound, and this, again, the hydroxide group is going to form a very polar compound. So option B is going to be my best choice because it is the least polar of my options, and I want something that will not dissolve something that has charges. So I want something that is non-polar, and so the carbon tetrachloride is going to be my best bet for the least polar option out of everything that I was presented. Gases generated in a chemical reaction are sometimes collected by the displacement of water, as shown above. Which of the following gases can quantitatively be collected by this method? So what we're going to do when we compare all of these gases to see which is going to be the best option for what we could capture within this apparatus is we're going to look at the general polarity and solubility in water. So if the gas or the compound is going to be very polar, then it's going to not do a good job not being in the water and separating itself, so that's going to be eliminated. So these with hydroxides are immediately going to be eliminated since we know that hydroxide groups are going to create some polarity. Hydrogen and chlorine, this is a very polar bond as well. So we are left with two non-polar substances, and we are looking to see which between these two is going to be the least polar between the two. So between hydrogen and carbon dioxide, hydrogen is a substantially smaller molecule, and we also have bonds between two of the same compound, so two of the same element. So this is going to be more nonpolar. We have less possibility for a London dispersion force, less interaction between the hydrogen and the water molecule, and so therefore hydrogen being the least polar option is going to be the best gas, the best compound available between all of these for this apparatus to collect. M plus is an unknown metal cation with a charge of +1. A student dissolves the chloride of the unknown metal, MCl, in enough water to make 100 milliliters of solution. The student then mixes the solution with excess silver nitrate solution, causing silver chloride to precipitate. The student collects the precipitate by filtration, dries it, and records the data shown below. The molar mass of silver chloride is 143 grams per mole. Mass of the unknown chloride is 0.74 grams. The mass of filter paper is 0.8 grams. The mass of filter paper plus the silver chloride precipitate is 2.23 grams. Which of the following diagrams best represents the silver nitrate solution before the reaction occurs? So this entire section of the question I don't care about at all. All I am asking is Which of the following diagrams best represents the silver nitrate solution before the reaction occurs? Remember that the water molecule is going to be in this kind of Mickey Mouse situation. These are my hydrogens, and this is my oxygen. Oxygen, we are going to have a partial negative, and my hydrogens, we're going to have a partial positive. So my silver nitrate is soluble, which means that we are going to have them separated into the silver and the nitrate ions floating in solution. So D is going to be eliminated since they are not separated. And then I just need to make sure that my water molecules are oriented correctly toward the silver and toward the nitrate. So the oxygen being partially negative should be oriented toward the positive silver, and the hydrogens being partially positive should be oriented toward the negative nitrate. That is going to be option choice A. Everything else has positives or negatives oriented in the incorrect direction, and that is all we needed to do for that problem. The survival of aquatic organisms depends on the small amount of oxygen that dissolves in water. The diagrams below represent possible models to explain this phenomenon. Which diagram provides the better particle representation for the solubility between oxygen and water, and why? So here we are looking at either some true hydrogen bonds going on here, or we are looking at just temporary dipole interactions here. The oxygen is going to be very non-polar, and so the hydrogen bonding is really relying on the polarity of both the hydrogen and whatever it's bonding with, the nitrogen, oxygen, or the fluorine. So diagram 2 is going to be a better model because water is polar and it can induce temporary dipoles in those oxygen molecules. Of the following organic compounds, which is least soluble in water at 298 Kelvin. So least soluble means that it is going to be the least polar. So looking at all of my options, I see hydroxide groups in 3 of them, so we can immediately eliminate those. Then between hexane and glucose, I see an oxygen present, which means I'm going to have more of an electronegativity difference versus just carbon and hydrogen present, where we have very nonpolar bonds. So the least polar is going to be the least soluble, so that would be hexane. Which of the following molecules is the least soluble in water? Again, we are looking for the least polar of the molecules. Any exposed oxygens, we have areas of polarity, so we can eliminate those. Then we have carbon tetrachloride here, and even though the bonds between carbon and chlorine are individually polar, since the molecule is very symmetrical, it is not going to be a polar molecule overall. Based off their Lewis diagrams, which of the following pairs of liquids are most soluble in each other? So we are looking for something that has matched polarity, so either something that is polar and polar or nonpolar and nonpolar. Here we have a polar water molecule, and then we have a hydroxide group, so we have polar and polar. So that's looking good. Then we have this carbon tetrachloride, which is going to be nonpolar, and water, which is going to be polar, so that's not going to work for me. Here we have a hydroxide group, which is going to be make this polar, and then we have carbon and hydrogen exclusively, which is going to make that nonpolar, so that's not going to work. Here we have a hydroxide group, which is going to make that polar, and then again, just carbon and hydrogen, so that's going to be nonpolar. So my only answer choice where I have the same polarities for both is going to be answer choice A. So that is going to be the compounds that are most soluble in each other. Which of the following substances has the greatest solubility in C5H12? 12 at 1 atmosphere. So C5H12, this is a bond between carbon and hydrogen, which means that this is going to be nonpolar. So I'm going to be looking for something that is nonpolar. Silicon dioxide, this is going to be just like slightly polar here. Sorry, I added too many dots there. Just slightly, we get some amount of polarity between the electronegativity difference, but we are symmetrical. So we are just going to have something that we have larger dispersion forces since we are a larger molecule. Then we have sodium and chlorine. The sodium chloride ions are going to be fully ions, so they are very polar. Water is notoriously polar. Carbon tetrachloride, very much nonpolar. We are very symmetrical. Even though the individual bonds between carbon and chlorine are going to be polar in themselves, and then NH3 is very polar as well. So looking between all of these, my least polar option, the thing that is going to have the least amount of differential between where the electrons live, is going to be the carbon tetrachloride, and so that is going to be the thing that is going to be the most soluble inside of that C5H12 compound. A student places pieces of iodine in 50 milliliters of water, another piece of iodine of the same mass in 50 milliliters of C6H14, and shakes the mixtures. The results are shown below. What do the results indicate about the intermolecular interactions of the substances? So we have the iodine in water and then the iodine in that carbon compound here. So iodine is going to be very nonpolar, and the water is polar. So iodine and water are not going to mix because we have a polar and a nonpolar, versus iodine and the carbon compound where we have nonpolar and nonpolar. So answer choice B, being iodine and that carbon compound have similar intermolecular interactions because we are both nonpolar, versus iodine and water, which do not, since they are polar and nonpolar, respectively. Silver plus chloride goes to silver chloride. A student mixes dilute silver nitrate with excess sodium chloride to form silver chloride, as represented by the net ionic equation above. Which of the diagrams best represents the ions that are present in significant concentrations in this solution? So the ions are going to be the things that are not dissolved. And so we are going to have initially silver nitrate and just a little bit of silver nitrate and a lot of sodium chloride. So after the reaction goes through and we have precipitated out the silver, I should not see any silver left in my solution diagram. So I'm going to eliminate choice B and D since silver is still present. And then what I'm looking for is, okay, who should be left over? We had a lot of the sodium chloride and just a little bit of the nitrate. So I should still see some chlorides that weren't taken out by the amount of silver that was present, but the nitrate should still be present. So since option choice A doesn't have any chlorines still left over, I'm going to go ahead and eliminate that choice. And I'm going to say that option choice C is correct, since I should see sodium and nitrate, since those are both soluble. And then since we had an excess of the chloride ions from the sodium chloride, I should still see some chlorines in my solution. So option choice C would be my best bet. Which of the following compounds is least soluble in water? Again, we are looking for the thing that is going to be the least polar. So anytime that I see hydroxide groups, I can go ahead and say that those are polar, which means that they are going to dissolve in water. I see oxygen and nitrogen here. Those are going to create some areas of polarity versus just a strictly carbon and hydrogen compound, which is going to be completely nonpolar and therefore not soluble in water. So that's going to be my least soluble compound, and that would be my answer choice.